This is the fourth block of topic 25, and in this lesson we're going to look at connections between the formulas for surface area of cones and pyramids, and also for formulas for prisms with cylinders. So we are looking at the net of a cone here, and we're wanting to know what could we call the name of this partial circle that creates the lateral face of a cone. So you may be able to imagine that if I continued this green arc, I could make a full circle, and that this point right here would be the center of that circle. And so L is the radius of that circle. So this section right here is what we call a sector of a circle that we have learned about, which really just means a portion of the circle. So how do we find the area of a partial circle? We have learned that how to find the area of a sector of a circle. It's just a fractional part of the area of the whole circle. So D is thinking to herself that she doesn't know how to find the area of a partial circle, but she thinks that she can find the length of the cut that looks like it's the radius of the circle. Remember, that's what is labeled as L here. So she imagines it back as a cone here, and that L is this slant height of the cone. And so if we know the height of the cone and we know the radius of the cone, we can complete this right triangle, and the slant height of the cone is the hypotenuse of that right triangle. So we could answer question 1 in our notes, which is just using Pythagorean Theorem to find the slant height. So remember, Pythagorean Theorem is leg squared plus leg squared, and the legs are the ones that make the right angle together. So that's the 2 and the 4 that are your legs. So leg squared plus leg squared equals hypotenuse squared. And our hypotenuse is the slant height, and we use a cursive L for that. So we know 2 squared is 4 and 4 squared is 16, so we can add those and get 20 for the slant height squared. But remember, we are wanting just the slant height, so we need to take the square root of that 20. So you have a couple of options here when you get to the square root of 20, and it depends on what directions you are given, either to round that as a decimal or to give it as a simplified radical, which it is neither right now. So if you're asked to round, you would of course just put the square root of 20 in your calculator, and whatever place value you're asked to round to, you would just round that. So I know there's a glare on that. So if we're rounding to the nearest tenth, it would be approximately 4.5. If we're not given rounding instructions, remember that you always will simplify radicals. And so the largest perfect square factor of 20 is 4. 20 is 4 times 5. So we can take the square root of 4, bring it out as a 2, and it is therefore exactly 2 square roots of 5. And of course, both of these are centimeters in units because it's linear. All right, so let's move on here. So question 2 in your notes, it says, so if all of the circle were here, its area would be 20 pi centimeters squared. So she found that using the exact length of the radius, which was the square root of 20, which is 2 square roots of 5. But if you multiply the square root of 20, or use it as the square root of 20 and pi r squared, it's actually a little bit easier to see. So you would have the area is pi r squared, of course, for a whole area of a circle. And if we use the radius as the square root of 20, it really makes it easier to see when we put it in here and square it. So we have the square root of 20. Sorry, I know this isn't very neat with me doing it with the mouse. But we have the square root of 20 that we're squaring. And of course, the squaring and the square root simply cancel out each other. And so that's how she quickly saw the area to be 20 pi, and of course that would be centimeters squared since its area. Its circumference would be 2 pi r, and she's using the unsimplified version of the radius as the square root of 20 there, and says that it would be 2 pi square roots of 20 centimeters. So she wonders if there's a way to figure out what fraction of the circle is present or is missing. And again, she focuses on what she can find, the circumference of the circular base, which is equal to the arc of the partial circle. So she knows the circumference of the base is 4 pi. This part right here came from around the circle. And we knew the radius of the circle was 2, so that whole circumference was 2 pi r, which is 4 pi. So she knows that the circumference of this base is 4 pi, so she knows the arc length of this partial circle is also 4 pi, because that's where it came from. So she says, wait a second, could the ratio of this arc length to the whole circumference of the partial circle, if completed, be the same as the ratio of the partial area to the whole area? And the answer to that is yes, that was exactly what it is. So the partial circumference is 4 pi, and she knows the whole circumference. We found that up here, 2 pi over the square root of 20. And so she gets a decimal approximation of that by dividing 4 pi by 2 pi square roots of 20. Now remember, if you were putting this in your calculator, it's really important that you put that denominator in parentheses. So you would have to put the 2 pi square roots of 20 in parentheses for your calculator to actually compute that correctly. So don't forget the parentheses around that denominator. So she said that looks about right. The partial circle is just under half of what it would be if it was complete. So half would be 0.5, and 0.447 is really close to that. So the area of the partial circle is 0.447 of the area of the whole circle. And we know the area of the whole circle. Remember, we found it up here. 20 pi is what we found it to be. So in a decimal approximation, that's approximately 28.1 square centimeters. So if that's correct, the surface area of the entire cone would be the area of the lateral surface, which she found to be approximately 28.1, plus the area of the circular base, pi r squared, would be pi times 2 squared, or 4 pi. And so if you put that in your calculator, that's approximately 40.7 as a rounded decimal. And that's centimeters squared because it's area. So let's look at question 3 in our notes. It says, remember the formula for lateral area for pyramid, which led us to the lateral area formula for cones. So the lateral area was 1/2 the slant height times the perimeter. And remember, this really should be a capitalized P because it's something we have to calculate. And that led us to, for the cone, the perimeter of the cone is the circumference, 2 pi r. So when we replace perimeter with 2 pi r, these 2's cancel out, and we are left with the lateral area, or the slant height times pi times r. And we usually put the pi r first. So we write that as pi rl. So D says, let me try one more thing, remembering how she conjectured a formula for the lateral surface area of a cone based on the connection between lateral surface area of a square pyramid and the perimeter of a square base. Any bets on whether I'll get the same result, which is approximately 28.1 centimeters, that's what we found. Where was that? Right here. Using the formula I derived. And so she writes, the lateral area of a cone is 1/2 the slant height times the perimeter, which we know simplifies to pi rl. We know the radius is 2, and remember on number 1 in our notes, we found the slant height unsimplified to be the square root of 20. And so we could put that into our calculator to see if we get that same 28.1. So we have the, can't see it now. Pi times 2 times the square root of 20 is what we're putting in our calculator. So pi times 2 times the square root of 20, and looky there, we do get the same thing, 28.1. So she's feeling great having figured out the volume and surface area for the cone-shaped chocolate that she is planning. So she calls to check with Miss Postulate, and Miss Postulate knows that Dee will face more cones in the future as she designs more chocolates. So she helps Dee generalize her approach for finding the surface area of a right cone, not an oblique, but a right cone. So by having Dee relabel her diagram of a right cone, Miss Postulate leads her to retrace her steps to see that her way of thinking did in fact lead to a generalization that is equivalent to 1/2 the perimeter times the slant height. So we have the slant height here as L. We know that this part came from the circumference of the circle, so it's 2 pi r, and that's what this circumference is here. So D generalizes what she has done by using a ratio of the arc length to the whole circumference. So remember that was 2 pi r over 2 pi L. Partial circumference would be the 2 pi r here, and the whole circumference would be the 2 pi times L. So you can see that the 2's cancel and the pi's cancel, and we're left with a ratio of r over L. That's the fraction of the whole circle that we're using. So the area of the partial circle is r over L times the area of the whole circle. This is our fractional part we want. And the area of the whole circle would be using this L as the radius, so pi times L squared. And of course, one of the L's here would cancel out the L in the denominator and leave us with pi RL. Now, pi r is half of the perimeter of the circle, or half the circumference. So that gives us the 1/2 p times L that we know we are using there. So she realizes she has already proven the last step true in her earlier explorations using perimeter equals 2 pi r, and so now she is ready for future cones. So let's look at question 4 in your notes. It says, during the call, Ms. Postulate also challenges D to apply what she's learned by considering a hexagonal pyramid, or hexagonal, however you want to say that. So D tries to visualize the connection between surface area of a pyramid and the perimeter of the base. So she makes a sketch of the right pyramid whose base is a regular hexagon, and then draws a net of it, visualizing how the perimeter could open up. And this is just one way of drawing that net. Here are the 6 isosceles triangles that are the lateral faces, and then the regular hexagonal base. So she notices that the top part of the net looks like half of a parallelogram. So if we had all of these again filling in these spaces, we would get a parallelogram. And so she knows that the base is equal to the perimeter of that base. So these sides of the triangles make up the base, which is the sides of the hexagon. So this came from the perimeter of the hexagon. So the base of the parallelogram is the perimeter of the hexagon. The height here of these, the pyramid, is the slant height of the pyramid. The height of the triangles is what I'm trying to say. The height of these triangles came from the slant height of the pyramid. That's a very straight line there, isn't it? So let's look at finding that. We'll do it, and then we can check it on the next page. So where's my little, oh, there we go. All right, so let's make this big on number 4. Okay, so remember this is the perimeter of the hexagon, and the height of the parallelogram is the slant height. So this, remember, since we don't have these sections filled in, the area of this parallelogram, when we do it as base times height, is perimeter times the slant height, but we don't have a complete full parallelogram. We only have half of one. So it'd be 1/2 times the perimeter times the slant height. And then we have the area, the surface area is what we're finding, of the pyramid is the slant height, or the slant height. How about the lateral area plus the surface area of the base? Well, that lateral area is what we just said, is 1/2 the perimeter times the slant height. The base is the area of the hexagon, and it's a regular polygon, so it's 1/2 apothem times perimeter is what we're going to be using on that. So that's all it's really asking us to look at here, is describe the relationship between the lateral surface area of a perimeter of the pyramid and the perimeter of the base. So the lateral area is 1/2 the perimeter times the slant height. And we can see that this is the same as we labeled our drawing, and that's exactly what she got. The lateral area is 1/2 the perimeter Remember, that really should be a capital P there for perimeter times the slant height. All right, so the next video we'll finish this.